Hello guys, welcome to the lecture 3 of digital electronics series. So as we discussed in the previous lecture, principle of duality, plus we have discussed about Boolean expression. Now we left with the consensus theorem and DeMorgan's law. So what is consensus theorem? In consensus theorem, if you have a variable A and with B, or so in consensus theorem, if this expression is given, the simplified one is this one, right? So as you can see in the final expression, this is absorbed, right? So consensus theorem says if you have a variable here and not of in this is another variable, this is another variable, and these two Boolean variable are ANDed here, then this will be absorbed. Let's try to prove it. So how to prove it? Okay, can I write this one? A plus A naught, because A plus A naught is always 1, and if 1 is ANDed with any of the Boolean expression, it will remain same. So now expand this one. Right? Now take these two expression, these two literals. We'll take out AB common, 1 plus C, and in this expression take A bar C common, 1 plus B. So this is always 1, this is always 1. Right? So this is proved that this is absorbed. Right? So as we can see, this is not required. So this is considered to be non-essential. This is non-essential prime implicants. We will discuss in detail what is prime implicants, what is non-essential prime implicants, what are the prime implicants. So basically these are the prime implicants, right? These are the implicants. So this is non-essential prime implicants. Now next we will see DeMorgan's, or before DeMorgan, let's solve one problem. Okay, so this is the problem given. Now pause the video and then try to solve it. Okay, so now take the C common, A bar B bar plus B plus A, right? Why we are simplifying? We are simplifying because we want to have less number of literals, less number of gates, so that the cost will be minimum when we will design the circuit. Okay, so a bar b bar plus b plus a. Now we can distribute this b here, so we can apply distributive property here. Right? This b plus b bar is always 1. Never cancel out these two. Like this is a naught and a. What somebody does always, if this is c and c plus, they just cancel out. No. This is always 1. So this is 1 plus b. Right? And 1 plus b is always 1. So the c. Now as you can see, this entire expression has how many gates? AND gate, AND gate, OR gate, AND gate, OR gate, AND gate, right? And we have NOT gate also. So instead of making a bigger circuit, the output is just C, right? Now let's move to DeMorgan's law. So before DeMorgan's law, let's see what is the complemented form of any expression. Complemented form of Boolean expression of function. So let's say we have f of x and y, x bar, y bar, x, y, right? So in complemented form, what we always do, if there is a not of any variable, just make it true. So this will become x. Instead of AND gate, use OR gate, right? And instead of y, it will be y not, it will be y. Instead of this not, this OR gate, this will be AND gate. Right? So what is this? This is F complement. We have come up with F complement. Right? Now let's see. Just remember this F complement. Now what is DeMorgan? DeMorgan's law. If you have x dot y naught, this will be equal to, right? If you have x plus y and you are doing naught, what is this? X naught. So basically in DeMorgan's law, you always compute the complemented form of that expression. How? Instead of x, you are putting x bar. So we want to compute DeMorgan's law for xy. We want to compute, not DeMorgan's law, we want to compute complemented form of xy. So complemented form of xy is this one. And the function which I am trying to do complement, it is equal to the this one, right? As per DeMorgan's law. So what I am meaning to say, if you have any function, right, and you do DeMorgan's means complemented form, what it will generate? It will generate F complement, right? And if you do duality, it will generate FD, right? And in this, from F bar, from complemented form to FD, it is only literal complement. Only literal complement. So literal complement means only if there is a X bar, you need to write X only. If there is a Y bar, you have to write Y. And if there is a Y, you have to write Y bar, right? Not of that. So let's see this one. Let's take a function x dot y, right? We will first compute the DeMorgan, that is complemented. What is the complemented form? F bar is equal to x bar plus y bar. Now, what is duality of this F? If you remember, in the duality, what we do, we only exchange dot with plus, that is and with or with and if there is a constant 1, instead of constant we put 0, and if there is a constant 0 we put 1, right? So I can also write that in duality these two are interchangeable and these two constant are interchangeable. We will not do any changes in the literals in case of computing dual of that function. So what is that dual of this function? We will only change operation and if there is a constant. But in case of complement, what are the things changes? Literals are also changed. The operations are also interchanged, and if there is a constant, then it is also changed, right? So in case of duality, what we will do, so FD for this, X will remain as X, no literal change in case of duality. In case of plus, it will be plus, dot, it will be plus, Y, it will be Y only. Now if you do literals change for this FD, so what is the literal change for this FD? Literal change for this FD will be, literal change is what? X bar. In literal change we never change the operation and we never change the constant. So X bar plus Y bar. Now you can see this F bar and literal change of dual of that function is same, right? So when we have a function, just remember thumb rule, for duality what we do, interchange plus operation with that and operation with or operation, and if there is a constant 1, it will interchange with 0, right? No literal change. And in case of complement, the literals is also change, the operations is also changed, and if there is a constant, that will be also changed. So if you have a function and you are computing the complemented form, complemented form will come, and if you apply literal change, it will come up FD. So you can see otherwise also in different this way also. You have a function complemented here. What is the literal change for this? Literal change for this is X plus Y, and X plus Y is equals to that FD. So remember, this is very beautiful concept, the duality and the DeMorgan's law, which is nothing but complemented form, right? So next we will see canonical form. Okay, canonical form. Canonical form of what? Canonical form of Boolean expression. Okay, now let us suppose we have a function given x, y plus y naught z plus z, right? So canonical form means for each of this implicant, all variables which is defined for this function, which is used as a domain variables for this function, should present in that literal. What it means, let us suppose in this literal only x and y is present, and this is a function of three Boolean variable. So in this literal, in this implicant, we have only x and y. G is not present here, right? So G should also present. So how to make G come up here, right? And here x is missing, here x and y both is missing. So what we'll do, we all know z plus z bar is always 1. Here x is missing, so x plus x bar. Here x plus x bar plus y bar, then z. Now expand it. Right, xyz, we can write xyz only, right? Xyz bar, there is no xyz bar, so this will be xyz bar. Xy bar z, xy bar z. X bar y bar z. So now in this Boolean expression, each and every term contains all these three variables. So this is the canonical form of Boolean expression. So in this is what? Sum of products, right? This is sum of products, right? So sum of products. This is not system.out.println. This is sum of products, right? So in a similar fashion, there could be product of sum also. So if you have given any expression, let's say f is equals to x plus y, x bar plus z, right? So I can write it in a canonical form. This is one implicant, this is another implicant. So this will be x, y. I can write z plus z bar. Can I? No. What we can write? we have x plus y over here, x bar z, in this we have missing z bar, right? So I can write x plus y plus z bar, x plus y plus z. How? This is p plus z, and this is p plus z bar and p plus z, right? Let me explain. Z bar always 0. We can take p common here, z plus z bar, which is 1. So this is p plus 0 and p, nothing but p, right? So we have taken p plus z and p plus z. So this was, I considered it as a p, right? So instead of p, I wrote p plus z bar and p plus z. So in product of sum, you have to be careful. So let's now see in detail canonical form. We have already seen what is canonical form. If in any expression, any of the implicant, it should have all variables with that implicants. Okay. So what is canonical mean term? So the same which we talk about that implicant, it is the same like canonical mean term. So if we have a function f, let's say a b c bar plus a bar b bar and c. So this is canonical mean term. This is canonical mean term. Okay. So in this canonical mean term, and what is this disjunctive normal form? So this is disjunctive normal form. That is sum of all canonical mean term. So this is canonical mean term, right? Now sum of products. So this is sum of products. So this f is disjunctive normal form, right? Now this function, disjunctive normal form means this function f will be true only if any of the disjunctive normal form value is true. So it means either this one is true or this one is true. How? Let's see. We have three variable here, right? 0, 0, 0, right? 0, 0, 1, 0, 1, 0, 0, 1, 1. You can see the pattern. This is a C variable. So these two are toggling here when B is 0. When B is also 1, so B is also toggling. So for B equal to 0, C will be 0 and 1. For B equal to 1, C will be 0 or 1, right? So for A equal to 0, B will be 0 and 1. And for each B, it will be 0 and 1. So the total number of, okay, I'll see in the next video. We'll see some numerical problems on this. So after this, this will be 1, 0, 0, 1, 0, 1. So this entire thing, this will be repeated. This was for 0, so this will be repeated for 1 also. Right. This is nothing but 0, 1, 2, 3, 4, 5, 6 and 7. 0 to 7 in decimal format. So it is saying A is 1. A is 1 here. Here. Now B is also 1. So B is 1 here in these two. So we are filtering out. We want to know which is this A, B and C bar. In this, out of 8 rows, which rows belongs to this? So A, B, C bar. A is true, B is true, and then when we will explain Carnot map, you will understand easily. In this, you need to find like this. A is true, so okay, this one. So now we have to filter out from this one. Now move on to B. B is true. This here in these two. So now we are filtered with only 2 rows. Now C bar, that is C bar, this one. So this is the row where this function could be 1. And what is A bar, B bar, C bar? A bar, B bar and C, this one. So if A, B and C, if it is 0, 0, 1 or 1, 1, 0, then only in that case F will be true. Right? So this is what I can write F as a sigma of this is 1 and this is 6. Right? Maybe it is not visible. I should write here. F is sigma of 1 comma 6. This is what? These are the mean terms. These are the mean term. Right? Canonical mean term 1 and 6. And this is sum of product. This is disjunctive normal form. Okay, and this F will be true only if any of these two mean term will become 1. Right? So similarly, there will be product of sum. Okay, so we will see in next lecture. So thank you guys. Hope you liked it. Please do share, subscribe and like also. Thank you.